Okay, so we talk about permutation today. So basically we have seen some mapping. So now permutation is a mapping, it is basically a bijective mapping. So let S be a non-empty set, non-empty finite set of element, then any bijective mapping from S to S any bijective mapping or function from S to S is called a permutation. Okay, it is basically a bijective mapping from the set to itself. So, any such mapping, any such function is called a permutation. So, this is the definition of permutation. And this is defined on a finite set of elements. Okay. Now, for example, suppose we have n elements. Suppose S is finite. So, suppose these are the elements, suppose there are n elements in the set, and suppose you have a bijective mapping S to S, then that means A1 is going to f of A1, A2 is going to f of A2 like this. So, we have AI is going to f of AI dot dot dot, An is going to f of An, and this f is a bijective mapping. So, that means this is basically nothing but this set, same set S. So, this collection is basically equal to S, and this collection is also S. So, S is going to S. So, this can be written in some other way, like in this form A1, A2, An, and this is AI say, and here f of A1, f of A2 dot dot dot, f of AI, f of An. Okay. This is basically a rearrangement, because this is a bijective mapping. So, this will be also onto. So, this will cover whole set S. So, this is our S, again this will be our S. So, any rearrangement is a permutation. So, that will gives us a mapping, bijective mapping 1 to 1. So, there will be no repetition in the this. So, that is why it is a distinct sets, distinct points, and it is onto. So, it is covering all the elements. So, this is nothing but S again. So, it is in some order. So, AI1, AI2, AIN. So, this is basically a rearrangement. Basically, AI1, this set AI1, AIN, this set is basically S. So, in some sort of rearrangement. Okay. So, this is called a permutation, also written as this. So, F is basically this. So, any bijective mapping from S to itself will give us a permutation. So, we can take some example, like if we have 4 elements, so like if S is say 1, 2, 3, 4, and suppose we have a bijective mapping like this, F1 is going to 3, F2 is going to 1, F3 is going to 4, and F4 is going to 2. So, we have 4 points 1, 2, 3, 4, and here we have 4 points 1, 2, 3, 4. So, this is S set, this is S set, this is the mapping. So, 1 is going to 3, 2 is going to 1, 3 is going to 4, and 4 is going to 2. So, this is a 1-to-1 mapping, and also it is a on-to. So, this is a bijective mapping, this is a bijection. So, it is a permutation. So, how we write this permutation in this that form of this 1, 2, 3, 4. So, 1 is going to where? 1 is going to 3, then 2 is going to 1, and 3 is going to 4, and 4 is going to 2. So, this is the permutation. Okay. So, any bijective mapping from S to itself can be written as a permutation. So, then we talk about inverse permutation, whether this is also a inverse of this function is also a permutation or not. So, let us talk about that. So, how many rearrangement is possible if there are n elements? How many permutation are possible? There are factorial n permutation are possible. So, basically there are factorial n number of bijective mapping from S to itself. Okay. Now, suppose you have a permutation f from S to S. So, that means basically we have a bijective mapping f a1, f a2, f a n. Now, we know if f is bijective, then f inverse exists. F inverse is basically from S to S again, and if f is bijective, we can show that f inverse is also bijective. This is a bijective. So, if f is bijective, we know the f inverse is also bijective. Okay. Now, what is how to get f inverse? F inverse is basically we will follow the reverse way. Like if we have, say for example, if we have this permutation 1, 2, 3, 4, and if say 1 going to 2, 2 going to 1, 3 going to 3, 4 going 1 going to 3, 4 going to say 3 going to 1, and 4 going to 4. Suppose this is our f, then what is f inverse? F inverse basically from this to this, like if we apply f compose f inverse, compose we will define on the permutation is basically composition of two functions. So, that means f inverse is 1, 2, 3, 4. So, basically 1 is going to, so who came from 1? 3 came from 1. So, 1 is going to 3 under f inverse, then 2 is here. So, 2 came from 1. So, basically so 2 is going to 1, 3 is here, 3 is going to 2, and 4 is remain unchanged. So, this is basically our f inverse. Okay. So, and this is also a bijective form mapping. So, this is a inverse permutation. Now, we define composition of two permutation. So, suppose we have two permutation f and g. Say f is say a1, a2. This is our set f of a1, f of a2. These are the images, and we have another permutation say g, a n, g of a1, g of a2, g of a n. Okay. So, f or g two bijective function from S to S. F or g are two bijective function from S to S. Now, we want to know their composition of two permutation. So, that means g compose f say. So, we know composition is a function from S to S. This is our S set. So, for this is all the S sets. Now, f is a function from, so this is a I, f is a function from here to here, this is f, so this is f of a I. Now, on this f of a I we can apply the g, so this will give us, this is a g, so this will give us g of f of a I. Now, if you consider the mapping from a I to this one, so this is basically called composition, g compose f, because we are applying f first then g. So, this is basically g compose f of a I is nothing but g of f of a I. This is how we define the composition, and we know this, if f and g are both bijective, then this is also bijective. Now, this is bijective and this is bijective, then we know this is also bijective. Now, once this is bijective, this is called a permutation, and how we define this in this way, this is basically A1, A2, say AI, AN. This is G compose F permutation. Now, this is G of F of A1, G of F of A2, dot dot dot, G of F of AI. This is the ith G of F of AN. This is the composition. Okay. And if it is F dot G, then we first operate G, then F. This is the convention we use. So, let us take one example on composition. On a set S, suppose we have a set S, say 4 element 1, 2, 3, 4. Now, suppose we define two function, bijective function, basically two composition, two permutation, say 1 is going to 1, 2 is going to 3, 3 is going to 2, 4 is going to 4. This is G basically 1, 2, 3, 4, say 1 is going to 3, 3 is going to 4, 1 is going to 3, 2 is going to 4. So, any rearrangement will give us a permutation, that is a bijective mapping, and this is 2, 1. Okay, now, we want to know the G compose F. So, first we apply F and then we apply G. So, this is basically, first let us write a G 3, 4, 2, 1, or maybe we can directly do that 1, 2, 3, 4. So, how we do? We first apply F on 1, F on 1 will be 1, then we apply G of this. So, this will be 3. Then 2, we first apply F on, so we will go to the 3, then 3 will go to the 2. Then 3, so we apply F, it will go to 2, then 2 will go to 4, then 4 will go to 4 and 4 will go to 1. So, this is the scenario. Now, we want to know the this F compose G for curiosity. So, what is F compose G? F compose G is first we apply F, then we apply first we apply G, then we apply F. Okay, so, if we apply G on 1, so we will go to 3 and 3 is going to 2, then 2 is going to 4, 4 is going to 4, then 3 is going to 2, 2 is going to 3, then 4 is going to 1, 1 is going to 1. So, these two permutation is not same. So, that is why this composition of function is not commutative. That means, f dot g is not same as g dot f. So, this dot operation, this composition operation is not, we will define the commutativeness, commutative. Like plus is commutative, real number plus, because a plus b we can write b plus a, plus is commutative, but this operation is not commutative. Okay, so, now we define cycle of a permutation. So, we define cycle of, suppose you have a permutation f from S to S, and S is basically A1, A2. So, AI1, yeah, some some rearrangement. So, say AI1, AI2, AIN, some rearrangement on this. Now, we call this represent a cycle said to be a cycle of length r if we have this property, say we have some AI1 up to AIR, say length r cycle, such that the next one, that AI2 is nothing but f of AI1. So, this one is basically f of this one. So, this one is also f of this one. So, AI3 is basically f of AI2, like this, dot 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 AIR is basically f of AIR minus 1, and the last one is, this is again going to this. So, AI1 is basically f of AIR. Okay. So, this way if we can represent this, then it is a basically cycle of length r. It is basically coming back to same. Let us take an example of cycle. Let us take an example. Suppose we have a permutation like this, 2, 3, 4. There are 4 elements, and say 1 is 1, 3, 4, 2. Okay. Suppose this is a permutation. Now, what is the corresponding cycle of it? This is also a cycle. So, because 2 is going to 3 and 3 is going to 4 and again 4 is going to 2. So, this is, even writing in this way, we can write a permutation also in cycle way. Okay. The cycle means 1 is not there. So, 1 is going to 1, that is not in the part of this cycle, that means 1 is going to 1, then 2 is going to 3, 3 is going to 4, again 4 is coming back to 2. So, this is the meaning of a cycle. So, this is a cycle of length 3. Length 3. Okay. So, every permutation can be written as a product of cycle. Now, product of cycle, not only product of cycle of length 2, basically we will come to that, and cycle of length 2 is called transposition. Okay, cycle of length 2 is called transposition. Now, we will show a theorem where it is telling that every permutation can be written as the product of cycle of length 2. Now, suppose you have identity permutation. Identity permutation means A1, A2, say 4 we have 1, 2, 3, 4. So, this cycle means 1, 2, 3, 4. So, everybody is going to itself. So, that is why it is a one length cycle, and one length cycle, how we represent a one length cycle? Suppose A1 can be written as A1 to, so sorry, A1, A2 and then A2, A1. So, this is the composition mapping. So, what is the meaning of this? So, A1 is, so we first apply this. So, that means A1 is going to A2 and again A2 is going to A1. Now, if we have a cycle of length 3, A1, A2, A3. Now, how we will write this in the two length product of two length? So, this is A1, A3 and then A1, A2. This is the composition mapping. So, how to read? So, A1 is going to A2, then again A2 is going to A1 and A1 is going to A3. So, A1 is going to A2, A2 is going to A3. So, this is the way we write. So, every cycle of different length can be written as a product of this one. So, let us take another example. So, if we have say 1, 2, 3, 4, 5, 6 bigger permutation, this is 2, 3, 5, 6, 1, 4. Okay. So, first of all, how we write this in terms of the cycle? So, 1 is going to 2, 2 is going to 3, 3 is going to 5 and 5 is going to 1. So, this is one cycle is closing and then we have anything missing? Yeah, we have 4 missing. So, 4 is going to 6 and 6 is going to 4. So, this is the permutation we can write in the cycle form, and then again we want to write this is a two length cycle, product of two length cycle. How we can write this? This is 1 5, 1 3, this is composition 1 2 and then 4 6 we have. This is the product of transposition. So, any permutation can be written as composition of product of transposition, two length cycle. So, if the number of transposition is even, then we call this is an even permutation. If this is odd, we call this is an odd permutation. Okay. So, this is more or less some concept on permutation. Now, we will move to the next topic, which is called equipotent set. Okay, suppose we have two sets, let A and B, two sets. Now, we defined a relation which is called equipotent relation. Now, A and B are equipotent, We define this as this symbol equipotent if and only if there exists a bijective mapping. There exists a bijective mapping from A to B. If there exists a bijective mapping from A to B, then we say these sets are equipotent. That means, if we have a set A, if we have a set B, if we can define a bijective mapping from A to B, if there exists a bijective mapping from A to B, then we say this A to B sets are equipotent. Okay. So, now we consider set of all sets and then we will see this relation is a equivalence relation, this equipotent relation between two sets. So, for that, first of all we need to show this is reflexive. So, for that we need to show A is equipotent to A. This is obvious because if we have identity function, like if we define a function a to a such that a of a is equal to a for all a. So, that means a belongs to this relation. So, this is symmetric. Now, how to show this is reflexive? How to show this is symmetric? So, symmetricity means if A is equipotent to B, this must imply B is equipotent with A. Now, what is the meaning of this? With this meaning of this, there exists a bijective function from A to B, then only they are equipotent. So, then we know if A is a bijective mapping, then A inverse F is a bijective mapping, then F inverse exists. So, F inverse is also from B to A, and this is also bijective. So, that means this is symmetric. Okay. Now, if this is symmetric, then we can show whether this is a transitive property is satisfying or not. So, for that transitive, so we take two functions. So, we assume A is equipotent with B and B is equipotent with C. So, that means we have a function f, bijective function f b to c, and we have another bijective function g from b to, this is a to b and that is b to c. Now, if you take the composition function, this is basically a to c and this is also a bijective. If this is bijective, then this is also a bijective function. So, that means A is equipotent with C. So, that means this equipotent relation is a transitive relation. So, it is satisfying reflexive, symmetric, transitive. So, that means equipotent is a equivalence relation. So, this is telling us this is an equivalence relation. Okay. So, that means it will partition, this is the set of all sets, it will partition this in the equivalence classes, and in same classes. So, these classes, the elements who are having same number of points, this we defined as a cardinality. So, if A, B are in the same classes, their cardinality must be same, that is the way. Okay. So, this will give us the equivalence classes. Now, we define enumerable set, just another 2 minutes. So, we just defined enumerable, or this is also called denumerable. So, a set will be called enumerable if it is equipotent with the set of natural number, then A is called enumerable set. Okay. A set is said to be enumerable if it is equipotent with the natural number. That means, if there is a bijective mapping from N to A, if there exists a bijective mapping from N to A, then we call this is as this is a enumerable number. Now, then what do you mean by countable? Countable set means if it is either finite or it is enumerable. A set is countable if a set A, if A is either finite or A is enumerable. So, that means, if it is finite, it can be written as A1, A2, An, or if it is enumerable, then there is a function from f n to A. So, that means, the A will be written as some f1, f2 bijective mapping f n like this. So, that means a 1 a 2 like this a n. So, A can be written as the sequence form a 1 a 2 to a n. So, this is the definition of countable countable set. A set is countable if it is finite or if it is enumerable. Thank you.